site is weaker, so there will be a weaker vibration here and weaker excitation of the nerve fibers. So all that the brain knows about what's being heard is this series of messages, one after another. So these are coming down what are called label lines, individual nerve fibers, each tuned to a specific frequency. And it's up to the brain to then decide what those mean in terms of what frequencies are present, be they high or be they low, and just how strong each of them is. This is a strong response, that is a weaker one. The cells that do the detection are called hair cells. And this name is sort of unfortunate. It has little or nothing to do with the kind of hair that I'm losing. This is a much smaller scale device, and you'll see in just a second why they're called hair cells. Each of them is a cylindrical cell, and in the mammalian cochlea, each of them is tuned to a different frequency. So there's some 16,000 of these lined up, of which we see here only 100 or so. And so this will go around and around through 3 spirals, with each of them representing a slightly different frequency along the length. Individual hair cells, such as this one here, have this elaborate structure called the hair bundle sticking out of its top. And this is the mechanical antenna that actually responds to the sound vibration. Now, you can see this somewhat better in the experimental cells that we use. These are actually from the ear of a frog, because these cells are hardy and relatively easy to study. The cell, like other cells, has a membrane around it. It's about 25 micrometers in its height. It has a nucleus, it has mitochondria and other organelles. It isn't a nerve cell, so it doesn't have axons and dendrites as nerve cells do, but it does make synapses at its base, that is contact with these nerve fibers that are excited and carry information into the brain. And the key part of the cell is the hair bundle, this little cluster of processes sticking up out of the top of the cell. And that's seen to best advantage by looking down on it in the scanning electron microscope. So this shows this beautiful organ pipe sort of structure with 2 key characteristics. One is that there's always a short side to the hair bundle, and then the processes get longer and longer and longer as you go across. So it always has this neatly combed look, and it looks like a bevel on, say, a hypodermic needle. The other point is that these little hairs, the processes, don't stand bolt erect. They always tilt over towards each other, forming this sort of conical or teepee shape. And that, as you'll see in a second, is important because it means they can interact with each other at their distal ends, at their top edge. These little processes come in 2 flavors. There is one eccentrically located at the tall edge of the hair bundle, in this case with a 1 micrometer ball on the top. This one is called the kinocilium, and kino is meant to suggest kinetic, the idea that this is a cilium that can actually move actively. This is like the cilia on sperm tails and bronchial epithelia. It has what's called an axoneme with microtubules and a type of motor called dynein. But the ones that do the work, or all the rest, they're called stereocilia. They're anywhere from 20 to 300, in this instance about 60. The name stereocilia means a stiff or rigid hair, which indeed these are, as you'll see in a moment. So each of these has at its core a lot of the protein called actin, which also is a component of muscle. And this core of actin then has membrane folded over the same way that the fingers of a glove fit over your individual digits. This demonstrates the behavior of a hair cell or hair bundle when it's confronted with the mechanical stimulus. So here's a hair bundle of the living cell. I'm touching it with this glass rod, and when I do so, there are 2 noteworthy things that happen. First, the hair bundle moves, and moves as a unit, so it doesn't fly apart. And as you'll see, that's because there are various types of connections between the stereocilia. And secondly, the individual stereocilia don't bow along their length. Rather, they remain straight and pivot at their base. So if you look at this longest stereocilium here, it's quite straight at rest, and it's equally straight after a stimulus is applied. So if each of these remains straight, but they pivot at their base, it follows that there must be a shearing motion between them. In other words, 2 adjacent stereocilia in contact like this are going to slide or shear at their tips with respect to each other. And that's key because it turns out that that's where the action is. Various experiments showed that the transduction or conversion of this mechanical input, such as a sound input, occurs not at the bottom where these stereocilia bend, but at the top where they slide. The way this occurs is that there's an apparatus there called the tip link. So the tip link is a fine filament. It's made of molecules called cadherins. It extends from the top of each shorter stereocilium to the side of the next longer stereocilium in front. So there'll be a total of something like 40 of these in the hair bundles that I'm showing you now. The way in which these transduce the input is very simple. Each of these has at its base one or more likely two channels. These are mechanically sensitive ion channels. And as many of you know, a channel is a protein that sits in the membrane, and it has a hole in it so that ions, such as sodium and potassium ions, can go through it and carry charge into or out of the cell. And that's the way that nerve cells conduct electrical signals. So at rest, these tip links are attached to channels, but the channels are closed. They have a tiny little gate that's shown here in red. If one applies a mechanical force to the system, pushing it in the positive direction, that is towards the tall edge, there will be a shearing or sliding between the adjacent stereocilia as I just showed you. As a consequence of that, there'll be increased tension in each of these tip links. That pulls the channels open. So this is a really simple Mickey Mouse sort of transduction apparatus, but it has two really neat features to it. First, it's blindingly fast. You don't see any chemical reactions in this picture. Photoreceptors of our eye, by contrast, have dozens of very complicated chemical reactions that make them exquisitely sensitive, but make them much, much slower. You know, hundreds and hundreds of times slower. And secondly, there's no intrinsic threshold, by which I mean an arbitrarily small stimulus will cause some increase in tension, some increase in the probability that the channel is opening, some increase in the current flowing into the cell, and therefore some increase in the excitation of the system. So the great sensitivity of the system down to the nanometer level stems from the fact that any tiny stimulus can engender a response if the cell simply takes time enough to determine that it's really hearing something and is not being influenced by mechanical noise. Now, there's a striking consequence of this that I'll give you a brief demonstration of. Maybe, where's some light? Can you see me over here? This represents an ion channel. Okay, you can see there are no tricks. It's got a gate, it's got a core, and it has a tip link. So imagine that this is one stereocilium and this is the next stereocilium with the tip link bridging. What I've been telling you is that as you listen, as you make a sound, this apparatus moves back and forth, and every time it slides back and forth, the channel opens, and every time the channel opens, some ions run in, and produce an electrical response in the cell. Now, the prediction is the following. Let's suppose you came up and pushed on my arms, pushing in the positive direction to your right. As you push, you'll do some work expanding the rubber band, and it'll be the same amount if the channel is closed or if the channel is open. But the interesting thing happens if, as you push, you start with the channel closed, but as you push, the channel opens. Then the rubber band goes slack, and it tightens up again. So the prediction is there should be a narrow regime, a narrow position, in which the hair bundle becomes softer because this elastic band has gone slack, and there's less tension in the system. And so we can actually plumb that by doing experiments in which we apply mechanical forces to the hair bundle. Now, I brought a hair bundle with me tonight, thanks to the local police who didn't catch me, and if they did, I would have told them that you did it, that you acquired it. But the idea is we have a flexible rod, and this rod in reality is 100 micrometers long. The hair bundle is in fact, in this case, 100,000 times smaller than what I showed you here. So the experiments are somewhat less casual than what follows. But the idea is that you walk up to the hair bundle with this rod, and you push its tip varying amounts. And if you look, you'll see that this fiber that I'm pushing with is flexing a certain amount. So if I know how stiff it is and how much it flexes, I can say how much force I'm applying to the hair bundle, or how much force the hair bundle is conversely applying to me. So we can therefore characterize the mechanical properties of this device by this simple mechanism. So the way we actually do the experiment, thank you, Craig, is shown here. We stick the fine glass rod to the top edge of the hair bundle. We cast a shadow of that onto a photodiode, magnifying it about 1,000 times. And then we can measure this motion with a precision of better than a nanometer and a frequency resolution of better than 1 kilohertz. When we move the base of the fiber, it pulls the hair bundle in the same direction. But because the fiber is flexible, it bends back to your left. By measuring how much it bends and knowing how stiff the fiber is, we can determine what force is being produced. And I should say there's a neat trick also for calibrating the fiber. If you look at the fiber, you'll see that it has fine vibrations in its tip, even when it's not attached to anything. Now, when I give a lecture, that's because I'm afraid. But in fact, when you do this experiment, it's because of Brownian motion. It's because it's being bombarded by water molecules. And there are theorems that tell you how much vibration ensues as a result of water molecules at a particular temperature and relate that to the stiffness. So we can calibrate these fibers very accurately. When we do the experiment, we see what I mentioned. These devices are not linear. That is to say, the relationship between how much we displace them and how much force we apply does not follow a straight line. That's called Hooke's law. The force is proportional to the displacement. But instead, there's sort of a segue between this straight segment and this straight segment. This represents the situation with all the channels closed. Then the channels open, and this represents the segment with all the channels in the open state. Now first, this is a nice demonstration that the theory that I presented to you is probably right. This is the way the channels work. But it has two other interesting impacts. The first one's in music. As long ago as 1714, the Italian violinist Giuseppe Tartini noticed what he called third sounds, terzi suoni. They've since been called distortion products, difference tones, and so on, most commonly combination tones. He was tuning his violin, and he noticed when he played a high frequency F2, a lower frequency F1, he could of course hear those tones. He could hear the harmonics because he had a good violin, so he could hear the second and third harmonic. But he could hear things he knew shouldn't be there. He could hear F2 plus or minus F1, twice F2 plus or minus F1, twice F1 plus or minus F2. So he called these the doubles tones, which gave him, a sort of 1714 take on where they came from. It really wasn't clear what they were doing. But they're actually quite strong. In fact, they're strong enough that some subsequent composers in a number of different instruments have used them to create melodies. So Karlheinz Stockhausen, who also has scored things for machine guns and helicopters, did pieces in which two tone streams are played, but you hear a melody that's not being played because this nonlinearity causes this sound, 2F1 minus F2, to be heard by your ear, even though these two are really the frequencies being played. And the Hungarian-Romanian composer György Ligeti also made music of this sort. So I'll play you a short demonstration just to show you how strong these tones are. And the way the demonstration works is shown here. I'll play first a constant tone, F1. Then another tone that starts out high and descends, F2. The strongest tone, as I've already mentioned, is twice F1 minus F2. So twice F1, which is not being played, would be up here. And twice F1 take away F2 starts out with a small difference, but becomes progressively larger. So 2F1 minus F2 starts out low and progressively rises. So the way the demonstration is contrived, you'll hear a constant tone and a falling tone. They're really there, but you can also hear a rising tone that I swear is not there. So here they are. Let me turn this down just a bit. Now the descending tone F2. Now the two together. Listen for the rising tone, particularly towards the end. So I can hear from the snickers that a lot of you can hear it. Let me play that again. Okay, a reasonable fraction here. And there are people here, there are students and postdocs from my group who can assure you that I would never lie to you. That was probably one of them. It really isn't there, and you can do this in more scientific circumstances with independent tone generators, independent amplifiers, and so on. So it turns out that this phenomenon, rattling around since 1714, stems from that nonlinearity that I showed you. That is from the fact that the hair cell steals a little bit of energy in each half cycle. Each time the hair bundle moves in one direction, a little bit of the energy goes into opening a channel. Each time it goes in the other direction, that energy is recovered as the channel closes. And that asymmetry produces this nonlinearity. The other consequence of the nonlinearity, which is rather neat, is its use in clinical medicine. I mentioned that it was a problem for years and years to diagnose young kids, particularly newborn kids, who had hearing problems. This provides a solution. So you take a device that simply plays into the ear from a simple microphone two stimulus tones. One tone, F2, that's higher than the other, F1. They go into the ear, and if the ear is more or less normal, the difference tone, 2F1 minus F2, will be produced, and some of that will be reflected back out. So then you just need a very simple meter that says, yes, that tone is there, or it's not. Now, some kids who flunk this test will have other issues. They may have water in their ear canals, for example, something really minor. So 2 days later, next week, they're fine. The great majority of apparent problems turn out to be illusory. But the important thing is that this means within a few days of birth, you can spot a kid who needs to be looked at in more detail. And then one can use other techniques such as auditory brainstem stimulation and the like, evoking electrical responses to see if hearing is really normal or not. And if it isn't normal, then one can first of all look into surgery, secondly look into a cochlear prosthesis or implant, which I'll describe later, or possibly go with American Sign Language. But one way or the other, the child will be dealt with within weeks of birth, or at least months of birth. In other words, the child will be given language at the time when he or she is passing through the critical period and most needs to pick language up. So it's really been a very valuable breakthrough. So far I've described the hair bundle as a recipient of sound, basically a transducer that captures physical vibrations, say from the sound in the air, and turns them into electrical signals. But it turns out that the hair bundle does a lot more than that. It's part and parcel of what's called the active process. So the active process is something that's found generically in amphibians and reptiles and birds and in mammals. In other words, all the tetrapods, the four-legged animals, have it. And it has four characteristics. Let's suppose we look at the basilar membrane, we shine our laser beam on it, and look at it vibrating up and down at one particular position, and then ask how it vibrates as a function of frequency. So I'll look at the vibration as I play a high frequency, or as I play a low frequency, or other frequencies in between. And for any given position, I will find that there's a particular frequency that gives the biggest response. If now the animal dies, or more humanely, if one just compresses the blood vessels of the neck so that the ear is temporarily deprived of blood, the response falls to this blue curve. And this is a logarithmic scale, so it falls by 100 to 1,000 times. In other words, there's an amplifier normally present in each ear, like a biological hearing aid, that enhances the response 100 to 1,000 times. The second characteristic is frequency tuning. If we look at a normal ear, at one particular place, one particular frequency will give the best response. Again, if the animal loses its blood supply, that response falls. If we now turn the sound up 350 times, we will produce the same amplitude of response at the peak, but we'll get much broader tuning. And this is, in fact, the reason that hearing aids are so often unsatisfactory. Hearing aids make the sound louder, but they can't restore the normal biological sharpness of tuning. So one's ability to discriminate similar sounds deteriorates despite the hearing aid. The third characteristic, which is a little more obscure, is called compressive nonlinearity. The idea here is that if you make the sound louder by 10-fold or by 100-fold, the response doesn't grow as much. In other words, there's sort of a compression. And this is the trick that allows us to accommodate this trillion-fold range of power into only about a 2-fold range in output. And finally, and most weirdly, is something called spontaneous autoacoustic emission. 70% of normal hearing people have sound that comes out of their ears if they're in a quiet enough environment. So if you go into a sound booth and we put a microphone in your ear and there's no sound at all, the odds are 70% that one or both of your ears will emit sound. The typical emission is what's shown here. There'll be 3 or 4 peaks, some big, some small. The world's indoor record is a woman who had perfectly normal good hearing with 33 of these peaks. And some people have none at all. They're quite stable, so your left ear will be different from your right ear, but over years or even decades, they don't change much unless your ears are damaged, unless you are in a very loud environment, take one of the ototoxic drugs or the like. So what this is saying is not that it's useful to have sound coming out of your ears. The point of it is that the system has what's called gain control. If you're in a loud environment, you don't need this amplifier, so the system turns itself down. If you go into a quieter environment, it turns itself up progressively until you can hear a pin drop. And if you go into a super quiet environment, like a sound booth, it goes up to 11. And it then goes unstable and begins to vibrate, just as this public address system would if we turned it up too far. You would get feedback, hum, or howling. The ear does exactly that. So it's, again, an indication that the ear has an amplifier built into it and that system can go unstable. This is a demonstration of these autoacoustic emissions from a normal person. This is, of course, amplified a great deal, but in this case, there are 2 prominent emissions at these 2 frequencies. There's some other smaller ones. There's some background hissing, and you'll also hear heartbeat. You'll hear the stomach gurgling. You'll hear clothing move. Okay, so this is what you measure with, perfectly normal hearing. So it turns out that all 4 of these characteristics originate at the hair bundle. The hair bundle isn't just a passive receiver. It's, in fact, an active device that is producing each of these characteristics, and I'll show that briefly. First, amplification. If I apply the stick to the hair cell, as shown here, at first I measure nothing except vibration from molecules of water bouncing against it. But if I begin to move the base of this stick, the hair bundle begins to move in synchrony with the stimulus. So here the stimulus is being applied. We see oscillations of the base of the fiber. Now the hair bundle at the other end of the fiber begins to vibrate. You can see there's a nice one-to-one relation between the 2, but the hair bundle is vibrating twice as much as the mechanical stimulus. In other words, there's amplification in the system. And the amplification can be much bigger than this, at least a factor of 10, or with multiple hair bundles, factors of 100 or 1,000. Next, there's tuning. So for a particular hair cell and a particular hair bundle, there'll be one particular frequency at which the response is the greatest and the sharpest. And if we move to higher frequencies or lower frequencies, we'll see a smaller response. If the hair bundle is dead, if it's passive, we get this very diminished response. Third, there's compressive nonlinearity. So very weak stimuli evoke a very strong response. The response gets smaller and smaller. The sensitivity gets lower and lower as we go to higher and higher levels of stimulation. And again, a dead bundle just shows this passive behavior. And finally, the hair bundles can vibrate spontaneously. And that spontaneous vibration is what is necessary to produce